let's get started. Okay, so last time we said that different observers assign different coordinates t and x to the same event. Okay, and this was a point that kind of came up at the end where somebody asked, I believe it was Viper, asked, can you explain the causality condition where if two events are related by a space-like separation, then they can't be causally related? And I think the reason for this confusion was just that I didn't do a good job of explaining this point here. Because what I was doing is I was drawing these pictures, t and x, and then I was saying, well, if I take a Lorentz transformation, this thing moves along a hyperbola, right? And this makes you think that like there's an event that's changing. And the only reason for that it looks this way is because I was drawing the coordinates that an observer in the primed frame would assign to an event on the same graph, which is a pedagogical mistake on my part. A more accurate picture of what's going on is that you have t and x, and then you have some events, right? And I'm just going to, let's just say we have two events, and I'm going to call them A and B. And then in another frame, t prime and x prime, these same events have different coordinates, right? And so maybe, if I were to move this guy along the hyperbola, it would be like somewhere like here, right? But it's still B, right? It's still the same underlying event, right? It just has different time and space values, right? And what I was saying is that one way that you can visualize this is that if you were to draw where this point is in the primed frame and where the point is in the unprimed frame, if you were to just draw that on the same grid, you would see that the points move along these hyperbolas. So if this is the event B in the unprimed frame, in the primed frame, it will move to here. Okay? But it's still the same underlying event. I should still call it B. It's like maybe a light bulb pops there, right? Or something like that. That's the same underlying physical event, just different coordinates are assigned to it in different frames. Okay. Okay, so what this means in particular is that imagine that B is a space-like separation to A, right? And recall that the Lorentz transformation is a linear transformation. So what that means is that in the primed frame, A will still be at the origin, right? That's why I still drew it over here. Okay, so recall that for space-like separation, the events move along hyperbolas that look like this, right? So what that means is that this point here in the primed frame is going to move to here, okay? And what that means is that A and B cannot be causally related events because in the unprimed frame, B occurs after A, but in the primed frame, B occurs before A. So you can't have these events be causally related, because if they were causally related, or if somebody could say they're causally related, then in the unprimed frame, they would have to say that A caused B. But in the primed frame, they would say B caused A, and that's nonsensical, right? So for events that are separated by a space-like this space-time distance, by a space-like interval, they cannot be causally related. Okay. 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 So one thing I want to emphasize is that all standard questions in special relativity can be answered simply by applying Lorentz transformations. Okay, and let's just quickly go through that because there were some technical difficulties last time. So we have time dilation. So if this is t and x, and I have a clock that's moving along this path, right? And so this separation is delta t, and this separation is going to be v delta t, right? Because it's moving at a velocity v. So this is described by some 4-vector delta t, v delta t. Now I'd like to know what is delta tau, which is known as the proper time, which is the time that is read by this clock, by the clock itself that moves along this path. And if I want to do that, all I have to do is apply the Lorentz transformation, right? And I can just do that by, I just say that delta tau times t, and I don't care. The reason I put a dot here is because I really don't care what goes there. I'm only after the proper time. I don't care what this space separation is, right? So I put 1 minus v1, delta t, v delta t. This is going to be gamma times 1 minus v squared delta t. And that means that delta tau is gamma 1 minus v squared times delta t. And that means that delta tau is going to be delta t over gamma, because if I were to just simplify this, I would just get a 1 over the gamma factor. So this is the time dilation, and note that, remember that gamma is 1 over the square root 1 minus v squared, right? And this is greater than 1, right? So I'm taking the time that is read in the unprimed frame, like in the the time that is read in the frame that is watching this clock. I divide it by a number greater than 1, and I get the time elapsed on the clock itself. So what that means is that delta tau is going to be less than delta t. And what people will say about this is that moving clocks run slow. Okay, so length contraction. So here I have t, here I have x. So if I have a stick that is just sitting in my frame, if I were to look at the ends of this stick in my frame, right, those, and I'm holding it stationary, I'm just holding it there, right, then the world lines of these ends of the stick will just be these vertical lines like this, right, because it's just, they remain at the same location for all time, right? So these vertical lines that I drew are the world lines of the ends of the stick. And then this separation here is L, and I'll call it L naught. By L naught, I mean the length as measured in the frame where the stick is motionless, okay? So now we can ask ourselves, what is L prime? That is, if I have another frame that is moving relative to this one, what length do they measure? Okay, and again, you just apply the Lorentz transformation, okay? So they are going to measure, right, what will be the events, right, of their measurement, right? So they are going to measure the ends of the stick, right? So their events are going to be located somewhere along in these lines, right? Because they're going to be measuring the ends of the stick. But because they have to measure the stick at the same time, right? Because if you see a moving stick, whoops, if you see a moving stick, so here's a stick and it's moving this way at some velocity v, right? You need to measure the ends of the stick at the same time. Otherwise, the stick will have moved a little bit, right? And you're going to get a distance that is going to be greater than the actual length of the stick. So they need to measure the ends of the stick at the same time. Okay, but events that occur at the same time in their frame do not occur at the same time in this frame that I've drawn here, right? In particular, this event is going to occur after this event, which you can understand if you think about, like, maybe I can come back to that. It's not super important for this derivation about which one comes before and which one comes after. The point is just that we know that simultaneity is relative, and it turns out that for the standard configuration where the frame is moving at positive velocity in the x direction, this will be the time ordering of the events, but it doesn't really matter. It won't affect your answer. Anyways, so what we need to figure out is we want to figure out the this is my pair of events, right? And I want to figure out what is the length that is measured between these two events in the unprimed frame, or sorry, in the primed frame. Okay, so I'm going to put 0 L prime. This is going to be in the primed frame. Gamma 1 minus V1 delta T L0. Okay, delta T is just going to be the time separation, is going to be just this separation here. Okay, and the reason that I put 0 here is because, as I just said, they need to measure the ends of the stick at the same time. Okay, so just applying very basic principles in the Lorentz transformation, you just turn the crank and then you'll get the answer. So here I'll get delta T minus V L0, and I'll get minus V delta T plus L0. Okay, now in order to get 0, I have to have that delta T is V times L, V times L0, right? And that means that if I now read the bottom equation, right, I will see that L prime is going to be gamma times minus V times V L0 plus L0. And then if I simplify that, that is going to be gamma times 1 minus V squared L0, which is just going to be L0 over gamma. Okay, so this is this. And what this means is that L prime will be less than L0, and that's why we call it length contraction. Moving sticks are contracted because they're shorter. Okay, let's do something that seems maybe a little bit scarier, but it's actually very easy. Let's do addition of velocities. Okay, so we're in the unprimed frame, and we measure two events of some object moving at some velocity v. So it's going to have some small time separation and some small spatial separation. And we know that if we know dt prime and dtx prime, we can form those into the velocity, right? So we know that dt prime, dx prime is going to be gamma 1 minus v1 dt dx. And then if I push all that through, I'll see that dt prime is gamma dt minus v delta x. Dx prime is going to be gamma dx minus v dt. And dy prime is dy, and dz prime is dz. Okay, so the velocity in unprimed frame, I'm going to call that u. Okay, and then in the primed frame, I'm going to call it u prime, right? So I want to figure out what is ux prime in terms of ux. So this, by definition, is just dx prime dt prime. And I just take dx prime. Whoops. Move it over here. And I take dt prime. Put it over here. And then these will cancel. And then I can multiply this by 1 over dt by 1 over dt. And then I will get, I'll get dx over dt in the first term, which will be ux. And then I'll get minus v. And then I will get 1 minus v ux. Okay, so this is, and then you just do the exact same thing for the other components, and I'll spare you the algebra. You can find that this is going to be uy over 1 minus uxv, and uz prime is going to be uz over 1 minus uxv as well. Okay, let's do the twin paradox. So this was number 3. So we're just quickly going through all the standard questions and showing that they are you don't really need to have a whole book about these things. They all just follow from the Lorentz transformation. So the twin paradox, the setup, I'm sure you've heard it before, that you have some twin, and he's on Earth, and then he's going to stay on Earth. So he's going to, sometime later, he's going to be over here, because he's still at I'll say that the Earth is the origin. The spot that he's on at the Earth, I'm going to call that the origin. Okay? And then his twin takes a rocket ship, and he goes out at some velocity, and then he eventually comes back and he meets his twin. Okay? And the question is, who's older? Okay, and I should really put this in parentheses, in a quotation marks, because it's not really a paradox. And we'll see why it's not a paradox. I mean, in some sense, all of the paradoxes in physics are not actual paradoxes, and the task is just to figure out why. Okay, so who is older, right? What that means is that we want to figure out the proper time of each path, right? Because the proper time is the time that is elapsed by a clock that moves along each path. So the twin that stays on Earth, his clock is going to elapse in some way from here to here, and the twin on the rocket ship is going to elapse in some way from here to here, and we just need to find the proper time along each path. Okay, so let's just split this up into like little segments, right? So I'll just look at this small amount of time dt, and I'm going to compare. Let me just blow up this picture, right? So here I'm comparing the time distance, or the time elapsed, the proper time elapsed between this part, and then in the and then for the twin, his looks like this, right? So what are these? And these are different events, right? Because this event and this event versus this event and this event, and I just want to compare their proper time. Okay, so we know that in general, right? In general, for any proper time elapsed between some pair of events, we know that d tau squared is dt squared minus dx squared. Right? What I mean by that is that if I'm in some frame and I just have any pair of events, the proper time elapsed along this trajectory is going to be equal to this. And the reason you know that is because the proper time is the time that is elapsed by the clock, right? So if it's by the clock, that means that in the clock's frame, right, the space-time interval is just going to be d tau squared minus dx squared in that frame, which maybe I'll put it as a 0. But by definition, right, dx0 is equal to 0, right? Because you're moving with the clock, so there's no spatial separation between these events. So this is just generally true, right? So what that means is that, just put this to the side. What this means is that the proper time between these events over here is just going to be dt, but between these events here, it's going to be, well, at least its square is going to be dt squared minus dx squared. So that means that d tau is going to be dt times 1 minus v squared. Okay? And you can see, maybe I should put some subscripts on this so that you know I'm talking about different things. So this d tau is for the Earth twin, and this is for the rocket twin. Okay? So, and then just based on this, you can see that d tau Earth is going to be greater than d tau rocket, right? And the same argument can be applied to compare any proper time elapsed between any of these segments, right? So what that means is that the rocket twin experiences less time. He is younger, okay? The reason that people call this a paradox is they will say, well, look, like if I hop on a rocket ship, right, then I see my twin who remains on Earth accelerate away from me, right? So isn't there some symmetry between these two situations? And there is no symmetry, The reason that there's no symmetry is because this twin accelerates. They accelerate here, right? So there is a distinction between their frame and the Earth frame. The rocket frame is not inertial. So that's the reason it's not a paradox, is because there is no actual symmetry. However, it would be incorrect to say that the paradox is resolved because all of the time difference between these two paths is made up for in this brief non-inertial segment. That's not true, because as you can see that even for comparing these two segments, right, and this segment are both inertial, right, the time difference is still there, right? So it's really the total time elapsed along the whole path that solves the twin paradox. And the reason it's not a paradox, the reason you shouldn't have expected it to be a paradox in the first place, is because there's just no symmetry between these two frames. Okay. So now that's all we're going to do with just using the Lorentz transformation. Okay. So now what we're going to do is we're going to talk about relativistic mechanics. Okay. So in particular, we would like to know how do we define energy and momentum in special relativity? This will be our central question. Okay. Now, how do you define energy and momentum in the first place? Right? When you first take physics in high school, they just tell you, momentum is mass times velocity, energy is 1/2 mv squared, blah, blah, blah. They just sort of define these things. And they don't really tell you any sort of like deep reason why. And they show you through various arguments revolving around work and conservative potentials, or rather conservative force fields for which you can define a potential. They use all sorts of arguments along these lines to show you that if you make these various definitions for energy in particular, that it's conserved. And if you take force as your starting point, you can show that the force is going to be the time rate of change of the momentum. So therefore, the momentum that they define for you as mv is at least a good definition. But this is like a little bit getting things backwards. Or I mean, it's perfectly legitimate, right? Just make some definitions and then see that they're useful. But we'd like a deeper understanding of what we mean by energy and momentum. And that comes from something called Noether's theorem. Okay, so that's what we're going to talk about now. Okay. I just want to know, how many of you have not seen Noether's theorem before? And it's perfectly fine if you haven't. Okay, Viper hasn't. Feynman has. I think in the future it might be good to just let people like just speak rather than type. But we can set that up for future lectures. Okay, so some people have seen it. Some people have seen it a little bit. Yeah, I'm fairly confident that the way that you've seen it before is, at least it's not the way that I prefer, like the way it's done in like Peskin or other standard books. Like the way that I'm going to show you it here, I think is the most efficient and easy way of understanding it. And it's not some like personal pet project of mine, right? I'm not like inventing anything new here. This is something that is understood by, the pros, so to speak. And I'm just repeating what they have already done. And I really think that this way that I'm going to show you should be much more common in QFT textbooks and just textbooks in general. It's really not that hard to understand, and I don't understand why they don't do it this way. So that's what I'm going to proceed to do right now. Okay, so first I should just set the stage. So we have symmetries of the equations of motion. What do I mean by that? So suppose q of t, and by q, I'm going to stand for the collection of all the generalized coordinates, right? So, I could have a is 1, 2, all the way up to n. It's just any collection of generalized coordinates that determine the solution to the equations of motion, okay? So suppose q of t is a solution to the equations of motion, which I'm just going to write as EOM, okay? Then I'm going to have some recipe, right? Some baked-in recipe where I take q of t and I do something to it, and I obtain some new trajectory q prime of t, okay? And for the moment, I want you to forget relativity, right? We're not talking about relativity. We're talking about classical mechanics in complete generality. So this prime that I've written here does not mean like the primed frame or the unprimed frame. It doesn't mean that anymore. It just means some new trajectory that I obtain from the old trajectory in some particular way, okay? So this transformation is a symmetry of the equations of motion if q prime of t, make it look more like a t, is also a solution, okay? So that's what I mean by symmetries of the equations of motion. It's just that you take some trajectory, which I could, write it as like, here's some picture of a trajectory, and then suppose like I just translate it, right? So, if I were to plot this in the standard way that you see it in textbooks, where you see here's t, here's q, then suppose I just translate it, right? So I just make q bigger, and this will be my q prime of t. Okay, so translation will be a symmetry of the equations of motion, right? When anytime that this trajectory is a solution to those equations of motion, this is also a solution. Then we would say that translations are a symmetry of the equations of motion. Okay, now we could potentially have some much weirder transformation. That is not really, as easily described as translation. And in particular, this trajectory does not even have to have the same time endpoints. I could do some weird thing, some very weird, funky thing, where maybe it goes like this, and then the time separation, here is like TA and TB, and then this time separation would be some different, it would be some different times, right? So we're going to actually consider situations like this, right? So what I'm saying is that a symmetry is just something that you can do to these paths where after you do it to the path, you get another path that is also a solution, okay? So now I'm going to talk about something different but related, which is a symmetry of the action. Okay, so recall that the action, if you have some trajectory q between two times ta and tb, as I've drawn here, this is defined to be ta tb dt times L of q dot t, right? So I will say that the transformation q of t goes to q prime of t is a symmetry of the action, not the equations of motion, but the action, if s of q is s of q prime for any trajectory q of t, not just solutions to the equations of motion, right? Remember that when you do the least action principle in classical mechanics, you consider some trajectory, you consider a bunch of different trajectories, right? And not all of them, in fact, almost none of them, are solutions to the equations of motion. One of them is, and it's the solution that extremizes the action, right? So when you have an action, right, it's very natural, and in fact, you always consider trajectories that are not themselves solutions. So when I say I have a symmetry of the action, what I mean is that I have this for any q. Any trajectory, if I stick it into the action and then I deform it to get this new trajectory, I will obtain the same number after I run the action on that new trajectory. So that's what I mean by the symmetry of the action. Okay. So these concepts of the symmetries of the equations of motion and the symmetries of the action are related. And the way that they're related is that symmetries of the action are symmetries of the equations of motion. Okay? The reason for that is very simple. If you have some trajectory, like suppose we have a symmetry of the action, okay? And that means that if I take some path and then I deform it, I will get the same action. But let's assume that this path is a solution, right? So what that means is that if I were to consider other paths, like around it, right, then the difference between these paths and the solution path is going to be first order in the variation between these two things, right? That's what it means for this thing to be a solution. So then what happens if I just deform all these trajectories, right? And I deform them in the same way. Like suppose I do translations just to be concrete, which means that I just shift them up, right? So you can see here that this black line here will also be a solution because all of these actions for all these different paths take the same values as they did before. So if this path extremizes the action, so will this one, right? So it's a really basic statement. It's not anything deep. It's just that symmetries of the action, almost by definition, are symmetries of the equations of motion. Okay, so now we can state Noether's theorem.
There's a question in chat asking if the converse is false.
That's a really good question. So I'm not exactly sure. I've repeatedly thought about this and never gotten a simple answer. Yeah. So really, the reason to be suspicious that the converse is true is because a symmetry of the action is a much broader statement than the symmetries of the equations of motion. Because for symmetries of the equations of motion, the only paths that you care about are solutions. But for symmetries of the action, you can consider any trajectory. So that's why it seems suspicious that the converse is true as well. I'm not sure. What I'll do is between now and the next lecture, I'll think about it some more and look into it and see if I can come up with a more satisfactory answer. But Noether's theorem is stated in terms of symmetries of the action itself. So we're not really, it's a good question, but I don't have a good answer at the moment. But me not having an answer at the moment is not going to affect anything that we do. Okay. Okay, so Noether's theorem. To every continuous symmetry of the action, there is a conserved quantity. Okay, so I'm just gonna, I think the best way to understand what this means is to just work through it slowly and just see examples. So first I should tell you what I mean by continuous transformation. Okay, so I will say that my transformations act on configuration space. So what I mean by that is that here's your configuration space, and I'm going to put time in as well. So by Q, again, I mean the collection of generalized coordinates. There could be many of them. Like this could be some very high dimensional space, and I only have two-dimensional paper. So just use your imagination and think of this axis as containing every single generalized coordinate. So what I mean is that a transformation, it takes a point in configuration space and it just moves it to like here, say. And it does this to every single point. Maybe this one moves here, maybe this one moves here, maybe this one moves here, right? It's just something that you do to every point in configuration space. Okay? Now, how can I write that mathematically? What I mean, and by the way, notice that there are no trajectories happening here. These are just points in configuration space. Okay? What it means to say mathematically is that we can write this as Q will be transformed into Q plus epsilon delta Q, and T will get transformed into T plus epsilon delta T. Okay? Delta Q and delta T characterize the transformation that you're doing. Epsilon is a parameter. So in particular, when epsilon equals 0, that's the identity transformation. That's when you don't do anything. You just leave every point alone. Now you can make epsilon non-zero, make it like really small, and then you get some small transformation. And delta Q and delta T characterize what transformation you're doing. And in particular, to keep things completely general, they can depend on Q and T. They can depend on where you are. You can shift each point by a different amount depending on where you are. Okay. Now, every transformation on configuration space causes pass through configuration space to also transform. Just a very basic statement, right? If I have some path through configuration space and I take every point and I move it in some particular way, I will get some new path through configuration space. Okay, so let's do one. Well, now let's discuss some examples, right? So example, translations. What that would mean is that the transformation would be Q goes to Q plus some epsilon, and T would go to T. What that means is that in the language that I've just outlined here, this delta Q, that means that delta Q here is 1, and delta T is 0. Okay? Now, the reason that I will call this translation is that if I have Q and T, I have some paths, and I do this to every point on this path. These points just get shifted up, so then the new path would just be the same, look the same, just be shifted up. So that's translations. Okay, and it's translations by an amount epsilon. They're translating this distance here is epsilon. So the amount that you translate is the parameter of the transformation, as it naturally should be. Okay. We could also do time translation. So that would be Q would go to Q, and T would go to T plus epsilon. And it would be the exact same thing as we saw before, except the trajectories get shifted forward in time, right? And right, so it's pretty self-explanatory. Notice that in this example, that if I were to get the action of this path, it would be S of Q would be TA TB dt L of Q dot T, but S of Q prime would be equal to TA plus epsilon TB plus epsilon dt L of Q prime dot T plus epsilon, right? Because that would be what you would get if you would stick this trajectory into the same action, right? Okay, so another example, rotations. Okay, so now I'm going to plot I'm not going to plot time anymore. I'm going to plot like here's X and Y, right? And we just have some points and we're going to rotate it, right? So what that means is that X and Y will go into cos theta, sine theta, minus sine theta, cos theta, xy. Now, what should the parameter of my transformation be? Right? Does anybody have a guess about what the parameter of this transformation is? You can type it in the chat. Okay. Okay, so yeah, of course it's going to be theta, right? So what I should do, and that's why, again, this is a continuous transformation, because, you know, it's sort of like, almost don't even need to say, it's just there's one transformation for every theta, and theta is a continuous parameter, right? Now what we do, I was writing the parameter as epsilon for a reason, because it's going to be very small. We're always going to take it to be some small parameter. So what that means is I should make theta here very small. And then I should expand this transformation to linear order. So cosine of theta when theta is small, that's just about 1. And this will be epsilon, and this will, so I'm writing theta as epsilon, right? This will be minus epsilon and then 1. But then this is going to be x minus epsilon y, and this will be y plus epsilon x, which means that the transformation is x goes to x minus epsilon y goes to y plus epsilon x, and that means that delta y, remember what we said before, that these transformations look like this. So I'm looking here. So delta y, or sorry, this would be delta x, is going to be minus y, and delta y is going to be x. So these characterize the transformation, and epsilon is the small angle, which is the parameter. Okay, so all these transformations are continuous because they are characterized by a continuous parameter. It's the translation amount in space, or the translation amount in time, or the angle, or something similar to that. So now let's talk about Noether's theorem itself, now that we know what a continuous transformation is. So I'm going to sketch the argument for you. And then later, when I derive the full Noether current, people call the conserved quantity the Noether current, you'll see that it will actually work out as exactly as I said. But I don't want to like go through all the little details. because I think the actual argument is much more simple than the proof. And so I should just state things directly because I think it'll be more clear. Okay, so we have a symmetry of the action, and that's going to be Q goes to Q plus epsilon delta Q, and T goes to T plus epsilon delta T. And this causes the actual path to transform. Q of T is going to go to some Q prime of T. And now here's the really clever step. The really, really clever step. Remember that epsilon is some constant parameter. So now make epsilon depend on time. That's really the big brain move. Okay. By the way, how many of you have seen this big brain move before? People are thinking it's strange, huh? Yeah, this is what I want to see. I want to shake you guys up a little bit. Bubs is excited because he knows. Bubs knows. Okay. So what's going to happen when we make epsilon depend on time? Well, you know, this transformation will no longer be a symmetry, right? Because why would it, right? It's only a symmetry when epsilon is constant, right? Now Q of T goes to Q prime of T is not a symmetry. So S of Q prime does not equal S of Q. What does it equal? Well, you can kind of understand intuitively what it's going to be, right? For any path, S of Q is just some integral along the path of this thing here, right? So if I were to like think of the path as just broken up into like a bunch of little segments, right? If I make this T and I make this Q and I have some path, or I'll like break up time like this. So I'll call this dti, and these are like indexed by I, say. And then I have some points that are along some trajectory. And then I shift each one by some different amount. You can do any sort of crazy thing, right? What is the action of this? What is the action of the old path? I'm just going to delete this so I can move this up. Okay, S of Q, if I were to break this up, would be dti L of qi, and then the velocity will be q of I plus 1 minus qi divided by dti. Okay. So now what you see happens is that when you take qi and you just change it to qi plus epsilon times delta qi, and then you're going to take dti and you're going to change it, or well, this is equal to t of I plus 1 minus ti by definition. And then that is going to change to, if I just shift each bit, this will change to dti plus epsilon I plus 1 minus epsilon I, right? And you can see here that if you were to just, do this and put it into here and then expand everything, the only thing that you could ever obtain is things proportional to epsilon I itself or the difference between these two things, right? So what that means is that in general, and by what I mean by general is not just for symmetry transformations. After making, so these could just be some random transformations, right? Doesn't have to be a symmetry transformation. After making epsilon depend on time, S of Q prime is going to be equal to S of Q plus some integral over the original bounds, the original time bounds, because again, I am just expanding this thing to in powers of epsilon, and I'm keeping only the linear term. So this will be dt, and it will be a term proportional to epsilon, as I just said, times something, I'll call it A, plus epsilon dot times B. And this will always happen. Does this make sense to everyone? Okay. Well, Ash, I don't know. I mean, why do you think it's a big brain move? Because right now I haven't actually told you why it's a big brain move. It's going to come as a shock. Why would you do this? Why would anyone do this? Ash is ahead of you. Okay, fair. Yeah, maybe. Well, that's why I'm asking. Ash, why do you think this is a big brain move? Can you try? Yeah, sure. Why not? Yeah, that's why I'm asking. Yes. I have a derivative of epsilon under an integral. Okay. Go on. Okay, I know it's fair. You know, this is it is a big brain move, and it's yeah, I'm here to confront and intimidate you. That's my purpose in these lectures. Okay, let's try to see why this is a big brain move. Okay. So there's step 2. So number 1 is we have a symmetry. Now I'm going to break that symmetry by making epsilon depend on time, and then I expand the action. I get this, and that's going to happen in general. So now step 3. When epsilon is constant, then we have a symmetry, right? Because we said in step 1 that we have a symmetry when epsilon is constant. Then we broke it by making epsilon depend on time. So now if we just take epsilon to be some constant function, then we have a symmetry. Now let's look at what happens to this expression when epsilon is constant. When epsilon is constant, we get this. Right? Because this term goes away. Right? But if it's a symmetry, then we know that we need to have S of Q, right? Because it's a symmetry. But what that means is that epsilon, remember epsilon is constant now, so I can take it out of the integral. Yeah, equals 0. Okay. Now, this is a symmetry regardless of the path, right? Because remember, what we meant by symmetry of the action was that any path, right, if I deform it, is unchanged in its value of its action, right? And in particular, its action, or rather, that statement doesn't depend on what these time bounds are, right? I could consider some very short trajectory, right? So that means that A itself is 0. Okay? Then, if I go back to this thing, what that means is that that for a symmetry, making the parameter epsilon depend on time yields okay. So that's and this is true for all epsilon of t. Okay? Does everyone follow so far? Are there any questions? Okay, it doesn't look like there's any questions, so I'm just going to go on. Oh, Harmonic is typing. No, it's not. We're not saying that epsilon equals 0 is a symmetry. We're saying that when epsilon is constant, there's a symmetry. Harmonic says for an epsilon that depends on time, you said that it's only a symmetry of epsilon. Yes, that is correct, Harmonic. Oh, I see what you're saying, Witten fanboy. You were saying that why was I able to get rid of this term for a symmetry? That's because forget symmetry. Like when epsilon is constant, this goes away. And then furthermore, we said that when epsilon is constant, we have a symmetry. We put those two statements together. This is the conclusion. If A equals B equals 0, then isn't this already a symmetry independent of any assumptions? Yeah, that would mean that for whatever reason, this action is just insensitive to all possible shifts that you could make to the trajectory. And I'm pretty sure that the only way that that would happen is if the action is literally just some constant, like the Lagrangian is just, I don't even know what that would be. That would mean that any arbitrary deformation to the trajectory yields the same action. So that would be a pretty boring sort of theory. Is there a general form for what A and B look like? Yes, there is. And I will derive it. I mean, it just comes from uh, uh, taking the trajectory, deforming it in the way that I said, and expanding this to linear order in epsilon and epsilon dot. And you will obtain a general form for A and B, and I will derive that for you. So it looks like epsilon will always remain a linear function of t, or you can have no. Epsilon is just any function of time, any function at all. I start with this transformation here. I say it's a symmetry, and then I break that symmetry by saying I'm going to make epsilon depend on time. And I know just by just expanding things, right? Just forget anything that I said, right? If I just do this, have epsilon depend on time, and I expand the action, I will obtain this, right? And then I furthermore say that when epsilon is constant, it must be a symmetry. And that implies that A itself is 0. So that means that for a symmetry, if I break a symmetry by making epsilon depend on time, I will always obtain this for any epsilon function, not just linear or quadratic. Okay, so good. These are all good questions. So let's move ahead. So step 4. Make epsilon vanish at the bounds. Okay, and have Q of t be a solution to the equations of motion. So what that means is that if I have t here and I have q, I'm going to assume that this trajectory is a solution to the equations of motion. So exactly, harmonic. So typical variational assumptions, exactly. So then what I do is I consider the deformed trajectories q prime of t, and they're all going to look like this, right? They're all going to end at the same points here, right? So we're in a least action scenario, as Harmonic just said. Now, because I said that Q is a solution, that means that these deformed trajectories, right, they have the same action. Right? So S of Q prime is going to be equal to S of Q. Right? However, we know from before that we still have this. So if let me just copy this. Okay. So this whole thing is going to still be equal to this. Okay. And that means that the second term is 0. Okay. Then I can integrate this by parts, right? And integration by parts looks very easy because epsilon vanishes at the bounds. So I can say that this is equal to minus TA TB dt epsilon b equals 0. That's a b dot. Now, this is true, remember, for any epsilon function that vanishes at the bounds, right? So that means that I can apply the standard arguments that I use in classical mechanics, where I make this variation just only vanish in some or only be non-vanishing in some very brief time interval. And so then this means that b dot itself is 0. So b dot is the conserved quantity. Or sorry, b is the conserved quantity. That's why this is a big brain move. Yeah, of course you like it. Something would be very wrong with you if you didn't like it. This is maybe the best thing that there is. No. It's not just for translations harmonic. I never assumed that this transformation was translations, right? It's just some general deformation of the path. We assume the first derivative of the action of functional vanishes because it's a solution. Yeah, okay, yeah. Good. Witten fanboy is pointing something out. So recall that when I got to here, I assumed that I assumed this. Oh shit. I assumed this. No, damn it. Ugh. I assumed this, and I assumed Q was a solution. Right? So B is the conserved quantity only on solutions to the equations of motion. Yes, that's a very important point. Harmonic. So okay. So harmonic is asking, isn't this only a symmetry for transformations to space and time, right? Because that's what this looks like, right? I take space and I add something to it. I take time and I add something to it. The point is that delta Q and delta T can vary depending on where you are, right? So if here is Q and here's T, this point may move over here, this point may move over here, and this point may move over here. And by making delta Q and delta T depend on Q and T, I can achieve this pattern where like I can make some arbitrary shift, right? So it's not just for translations to space or time. It's for an arbitrary transformation. That's a symmetry of the action. Would it be correct to say that any infinitesimal general transformation, general quantity can be represented like this? Yes, that would be the case, Ash. I'm just going to go quickly get a cup of water. Proc says it's first order Taylor expansion. Yes, it's a first order Taylor expansion of the transformation. I'm just going to go, I'll be back in like 30 seconds. Just need to get some water. Pion says, do we mean partial mu? No. Nope. No. I mean, we're expanding in the parameter, right? This thing here is a first order Taylor expansion in the parameter. Not space or time. It's in the parameter. What are you doing? Somebody keeps calling me.
Ion was responding to the question of how does this derivation change if it becomes a field Lagrangian instead of just a normal standard one.
Sorry, who's asking that?
Harmonic originally asked how does it change if it's a field Lagrangian instead, and Pion was responding to that question.
Oh, sorry. Okay. I just misread. It's still the same thing though. It's always you're expanding in a parameter, and the parameter is not space or time or anything like that. It's an external parameter, right? It's an angle, right? Something like that. Okay. So let me just recap what I did here, right? So this gives us what is known as the Noether procedure. Okay, so one, you have a symmetry of the action. Q goes to Q plus epsilon delta Q. T goes to T plus epsilon delta T. And then you take this and you turn it into some deformation of paths, right? Because if you can deform every point, you can deform any path, right? Then it would just look like this, right? So you use this transformation that you have to have some deformation to the path. And because it's a symmetry, you'll have that S of Q as S of Q prime. Okay, then what you do is you make epsilon depend on T, expand S of Q prime. You should find dot B, and then 3 is B is your conserved quantity. So it's a simple three-step process to derive any conserved quantity from a symmetry. You just identify your symmetry. You you make epsilon depend on time. You expand, and by the way, when you do this, you don't need to assume anything about epsilon vanishing at the bounds or not, right? Like, we saw that this form was obtained for any epsilon function, right? We made epsilon vanish at the bounds later to argue that B was conserved, right? But to obtain this form, we did not need to assume that epsilon vanished at the bounds. So just make epsilon be any old thing, any old function. When you do this, when you find S of Q prime, you should find this, and then you just identify B as your conserved quantity, and it's as easy as these three steps. Okay, so this is the Noether procedure. Okay, so now we should do some examples. So we're going to say that time translation symmetry is going to imply energy conservation. Okay, so how are we going to do that? Okay, so what is time translation symmetry? That means that Q goes to Q and T goes to T plus epsilon, right? So let's now figure out what this does to any path, right? So if you have some path, Q of TT, right? I'm just writing the time coordinate and the rest of the generalized coordinates, right? This is going to become Q of T because I am not changing Q, and this is going to be T plus epsilon. Okay. But then I'm just going to relabel this. I'm going to call this just T prime. This would be Q of T prime minus epsilon, because T is equal to T prime minus epsilon, and this will be T prime, right? And what that means is that the new path will be Q prime of T, but that's going to be equal to Q of T minus epsilon. I'm just getting rid of this. I don't want to keep writing T prime, right? I can just relabel it as T. Is going to be that. And it's going to be, if this path is between TA and TB, this path will be between TA plus epsilon and TB plus epsilon. Okay, so this is going to be my new path. Okay, and now so that was step one of the Noether procedure, right? You identify what this thing is, and really I should also now explain the conditions for when it's a symmetry, right? It will be a symmetry whenever the Lagrangian does not depend on time. And you really don't even have to do any work to see that, right? Because if I have some action, right, and all I'm doing is I'm just shifting it over in time, right? If the Lagrangian actually depends on the time value, right, then these two paths will not have the same action, right? Because I'm not changing anything besides the time, right? So it's only the case that the Lagrangian is independent of time that this will be a symmetry. Okay, so that's step one. Step two is expand S of Q prime, right? So this is going to be TA plus epsilon, TB plus epsilon, dt times L of QT minus epsilon, and then the derivative of QT minus epsilon. Remember, I should have actually written this. Shame on me for forgetting to write this. It's the big brain step. Make epsilon depend on time. And then stick the deformed trajectory, where epsilon now depends on time, stick that into the action, and you'll get this. Okay? Then we need to expand this. Okay? And really the first thing that we should do is you should figure out what is this derivative. So if I have d dt qt minus epsilon, I just use the chain rule, right? That will be the time derivative of q evaluated at t minus epsilon times the derivative of the inside thing, which will just be 1 minus epsilon dot, right? Okay, and then what I will have, when I have my Lagrangian, I will have q of t minus epsilon, and I'll have q dot of t minus epsilon times 1 minus epsilon dot. And notice in here, everything is written in terms of t minus, everything is evaluated at t minus epsilon, right? And then I have these bounds here, which are at t plus epsilon. So I'm going to just change variables, right? Because ultimately, remember, in the Noether procedure, I want to I want to expand the action, and I want it to have the same bounds as the original path, right? Okay, so I'm gonna have my new variable be t prime is going to be t minus epsilon, and that means that dt will be dt prime times 1 plus epsilon dot, and then I just substitute this into my integral, and so that means that s of q prime is going to be now it's going to be ta to tb, right? Because when t is equal to ta plus epsilon, it's going to be ta plus epsilon minus epsilon. That's just going to be ta. So I have now the same bounds, and then I'm going to have dt prime times 1 plus epsilon dot times L of q of t prime, q dot of t prime times 1 minus epsilon dot. Okay, and now I can expand this, right? So are there any questions so far? Okay, it doesn't look like there are any questions. So now let's just keep expanding. So I'm just going to erase, because t prime is just a dummy variable, right? I'm just going to relabel it as just t, because who cares? And then here, I will have L of q dot minus dl dq dot times epsilon dot. This thing in brackets is just Taylor expanding this. Okay. Now I just, factor this out. This term, where I multiply the 1 by the L, that is just S of Q. Now I can, now I have 2 more terms, right? I am going to also have, let's do this term, right? So it's going to be epsilon dot times L, that's that term. And then I will also have this term, which is going to be minus dl dq dot epsilon dot. And then the last term that I could have is I could also have this term with this term, but that would be order epsilon dot squared. And we drop that, right? Because we're only expanding to linear order. And then as promised, right, I have obtained the form that I said we should obtain, which is we have epsilon dot times L minus dl dq dot, oh, sorry. When I expanded this here, somebody should have spoken up. This is going to be q dot, right? because I'm multiplying here, I'm multiplying q dot times this whole thing in parentheses. So okay, so this is going to be times q dot. And now look, this is our B. Okay, so that means our conserved quantity is L minus dl dq dot times q dot. And does anyone recognize this expression here? Yep, harmonic, it's the Hamiltonian. In particular, it's actually minus the Hamiltonian, right? And if minus the Hamiltonian is conserved, so is the Hamiltonian. So we have shown that energy conservation leads to, time translation symmetry leads to energy conservation. Now, I just want to point out that unless you're shitting your pants right now, I don't know what to tell you. This is quite literally, I mean, it's the great. I think Noether's theorem is the greatest thing. I mean, it's the greatest thing ever, right? It connects symmetry principles that we know and love, like time translation, to conserved quantities that we also have heard about since high school. It explains why these quantities are conserved and links them to a deep, deep thing about nature, which is that it doesn't care what time it is. It quite literally does not get better than this, people. Okay? So, please take a moment to collect yourselves and, regather your composure. And I'll wait because I can't imagine that you are doing all right now. Okay. Yep. Changing my pants as we speak. There's no shame in it. Okay. So let's do one more example, which is going to show us how even more broad Noether's theorem is than you might have thought. So okay. So this is our next task, is to investigate spatial translations. Okay. So spatial translations mean that Q goes to Q plus epsilon and T goes to T. And in particular, we can only have spatial translation invariance. Let's just consider one. Okay. Let's consider just like one particle, right? Just to keep things simple, right? We have one particle, right? Then the only way that we can have a symmetry of the action is if the Lagrangian does not depend on spatial translations, or it doesn't depend on Q, right? And actually, we can. I won't even assume that. We'll just derive that, right? Okay. So that means that Q of T goes to just Q of T plus epsilon, and this is our Q prime of T. And let's now calculate S of Q prime. This will be TA, TP, plus epsilon. Okay, right. Remember, make epsilon depend on time, and then substitute it in. So that means that this will be Q dot plus epsilon dot. If you didn't make epsilon depend on time, you would forget to write this epsilon dot, right? Because you would think that the parameter was constant, so its derivative would vanish. But remember, you always make the parameter depend on time first. Okay. Okay. So now, let's expand. Okay, and you might be concerned because, like, Nay, you told me that when I have a symmetry, I will only have a term proportional to epsilon dot. So what is this? What is this thing doing here? And the point is this, that I assumed a completely general Lagrangian here, so I didn't actually put in yet that it was a symmetry. Okay, so it's a symmetry when epsilon is. We can only have a hope of it being a symmetry when epsilon is constant. But that means that we need the this term to be 0. But that means that dl dq is equal to 0. Right, so I've just derived what I said earlier, which is that you can only, if you only have one generalized coordinate, right, only one particle, or one collection of generalized, it could be in 3 dimensions, say. If it's one particle, it will only have spatial translation symmetry if this is 0. Right? Okay. So that means that because we're going to assume we have a symmetry, assume L is just a function of Q dot, right? So that we have a symmetry. Okay. And then when we assume that L is only a function of Q dot, then this term goes away, and then we can identify this as our B, or rather, remember just the thing multiplying epsilon dot is our B. So this means that dl dq dot is our conserved quantity. And this is just the momentum, right? Okay. Now here, this is really going to blow your mind. Okay. What if you don't have a symmetry? Okay. Well, remember what we said earlier, right? That in general, right, when you expand, you're always going to obtain something like this, right? So it's only a symmetry when this A term is 0, right? If it's not a symmetry, then A won't be 0, right? And that's really the only difference, right? So if it's not a symmetry, then after you make epsilon depend on time, you're going to have this. And A will not be 0, okay? But if you go through the same arguments that we did before, what will you have is you will have, remember the next step in the argument was you assume that epsilon vanishes at the bounds, right? And when epsilon vanishes at the bounds, you will have S of Q prime will be equal to S of Q, but it will still be equal to this, right? And then that will imply that this is 0. Okay. Then I just integrate this by parts, right? And I get, under the integral, I get epsilon times A minus B dot, which will then imply that B dot is equal to A. So even when you don't have a symmetry, Noether's theorem is still useful. It tells you that the thing that would have been a conserved quantity is no longer conserved, but its time derivative is now just equal to A. Okay, and let's use this principle in time translate or in a spatial translation, right? Before we eliminated A, right? We said that dl dq was 0, but now let's assume that we don't have a symmetry, which means that dl dq is not 0, but dl dq is still our A, right? So what that means is that dl dq dot, the time derivative of this, is equal to dl dq, which is just the Euler-Lagrange equation, right? But in particular, suppose that you had, L to be equal to, 1/2 m q dot squared minus v of q, right? then dl dq will be minus dv dq, right? Which is just the force, right? So then using this principle that when you don't have a symmetry, B dot is A, you can show that ddt of P is just the force, right? And similarly, if you were to do like angular, if you were to do a rotation symmetry, right? Or rather, if you did a rotation but you didn't have a symmetry, you would find that the time rate of change of the angular momentum was equal to the torque. And you could derive the expression of the torque simply by making epsilon depend on time, doing this transformation, and identifying A as your torque. Does this make sense? So what I'm trying to say is that Noether's theorem is still useful even when you don't have a symmetry. It just is that this A term is going to be equal to the time derivative of what would have been conserved. Are there any questions? See somebody typing. You're being distracted by a mosquito. Do you know if there's any relation between this kind of statement and anomalies? Yeah, that's a good question. So I would guess that there is, because anomalies like come from like this like the fact that like the measure may change. But I've also heard that thinking about the path integral measure is like not the right way of thinking about anomalies. So I'm nervous about making that statement. Do I know what the right way of thinking about anomalies is? No, I don't. But just from people that I trust, I've heard that this is like not the right way of thinking about anomalies. Yeah. That makes sense. Yeah, I'm sorry, I don't have a good answer about that. Yeah. We can discuss later. Um, okay. Um, okay. So let's derive the Noether current in general, which will constitute like a full proof of Noether's theorem. And we'll also answer Bub's question about the general form of A and B. Okay. So that means that if I have some path, this will become okay. And then note that along the path, delta Q and delta T become functions of T, right? Because I know that delta Q, and if I think about it in this way, right, delta Q is just some shift that depends on Q and T. But when I'm assuming that when I'm assuming that we're on the path, right, this is going to be delta Q of some path evaluated at that time times T. But this is just some function of time, right? So both delta Q and delta T along the path are just functions of time. Now set T plus epsilon delta T equal to T prime. And then when I reparameterize the path, when I reparameterize this path, this will be equal to Q T prime minus epsilon dt plus epsilon delta Q. t prime. And notice that here, delta q and delta t are evaluated now at t prime minus epsilon delta t, right? I just don't want to write it because it'll be too many parentheses, right? So that means that q of t goes to q prime of t, which is going to be equal to q of t minus epsilon delta t plus epsilon delta q, and here I can write it here, just to make it clear that these are both evaluated at t minus epsilon delta t. Okay, so this is our new path. Now make epsilon depend on t, and we calculate s q prime. This is just going to be q prime of t d dt q prime of t, right, by definition. And let's just expand the derivative, because that's, always it's a useful thing to do. You're going to take the time derivative of this whole thing here. Use the chain rule. This will be q dot of t minus epsilon delta t times 1 minus the time derivative of the product, that plus the time derivative of epsilon delta q of this, right? Oh, and this is actually a very important point, right? You might think, like, why didn't you include like the product rule part here? Right? Why didn't you take the derivative of the inside function here? And the reason is that I could, right? But that term would be order epsilon squared because of this term here, or because of this epsilon here. So that's why I don't need to put like this thing here, right? Because that'll just be of order epsilon squared. Okay, so I just have this. Okay. Now everything here is evaluated at t minus epsilon delta t. So I'm going to do what I always do, is that I'm going to change variables. T prime minus epsilon delta t, t prime is going to be t minus epsilon delta t. dt will be equal to dt prime 1 plus epsilon delta t dot. And then I'm ready to substitute everything. So I will have s of q prime will be equal to ta to tb, now with the same bounds because I've changed integrals, or changed variables, right? And I'm just going to, everything that I wrote here is in terms of t prime, and I'm just going to erase t prime. I'm going to erase the prime, right? Because again, it's a dummy variable. There's going to be a lot to write here, and I don't want to have to write it and then write it again without the prime. So I'm just going to skip that step. So then this will be equal to 1 plus epsilon delta t dot times the Lagrangian q plus epsilon delta q, right? And notice that here, after I change variables, is just going to be q times epsilon delta q, right? And it's going to be evaluated at t, right? Because I've changed variable, right? So I'm just writing that as q plus epsilon delta q. And then I write this as q dot. I look at this expression up here, and I see q dot plus epsilon delta q dot minus q dot epsilon delta t dot, but then t is going to become t plus epsilon delta t. And then I just have some expanding to do, right? Because I just expand this, and I should get that this is equal to S of Q plus TA to TB delta T epsilon A plus epsilon dot B. And I just need to find A and B. Yeah, the dot is over both, right? Yeah, exactly. Yes, Witten, you're correct. Witten fanboy's correct. The dot is over both, yeah, and I just don't want to have to write out the product rule, right? That's why I'm still grouping them together. So when I look at this, I have, I'm going to have this times L plus DLGQ times something plus DLGQ dot times something, and I just need to expand this out. So A, what is A going to be equal to? A is going to be the terms proportional to epsilon. So there's going to be one term coming from this, right? Because I'm going to have an epsilon dot delta T plus epsilon delta T dot, and then this term multiplies L to give me a term proportional to epsilon. So that's what I mean by this term here. So this is going to be equal to delta T dot times L. And then I'm going to have the term, this term, right? So that's going to be DLGQ times whatever is in here proportional to epsilon. And if I look here, it's going to be delta Q. Okay, so there's that term. And then I have this term, which will be DL/dQ dot times whatever is in here proportional to epsilon. And when I look here, I see that I will have, what will I have? I will have a delta Q dot from this. And I will have a minus Q dot delta T dot from that. There's that term. Then the only other term that would be left would be, multiplying this by these two things, but those will be of order epsilon squared, so I drop them. Oh, and I forgot to write something here. So I have plus dl dt times that, right? So I still have this term, right? And that is going to be dl dt times delta t. Okay, so there's my A. So as Bubs, you were asking about the general form of A, this is the general form of A. And this is equal to 0 for asymmetry. Right? I mean, when you run the Noether procedure, you'll already have some explicit Lagrangian, right? So you don't, this A thing will not show up, right? But if you were to start with some general Lagrangian written, you're not writing down any Lagrangian in particular, this A is giving you a condition for when the transformation is a symmetry of that Lagrangian. It's when you write all this stuff out and it sums up to 0. Yeah, exactly. It depends on the variations. Yeah. Okay, so what about B? Okay, so I'm going to have this term, which will be delta T times L. And then I will have this term. And when I look here, I see that this does not have anything proportional to epsilon dot, so that's just 0. And then I have this term, which is going to be plus dl dq dot times whatever is in here proportional to epsilon. And it's going to be delta q dot. That's the first term. times the thing here proportional to epsilon, which is, or minus that, which is going to be q dot delta t dot. Or no, sorry, it's going to be q dot delta t dot. Wait. No. Q dot delta t, because the derivative goes on the epsilon. Yeah. I was concerned because units weren't working out. Okay. And then this is going to be L minus dl dq dot. If I just group the terms that are proportional to delta t, I'll have this times this plus dl dq dot times delta q. So this is my conserved quantity. It is always going to be, minus the Hamiltonian times the shift to time plus the momentum times the shift to q, right? And notice that these things can be some complicated expressions. As before, Harmonic was asking, isn't this just translations? It's not, because delta t and delta q can be some complicated functions of q and t, right? But whatever they are, you multiply this complicated function by minus the Hamiltonian, you multiply this complicated function by the momentum, and then you get your conserved quantity. Okay. Does this make sense to everyone? Oh, sorry, I've dropped a q dot here. Very good question, Harmonic. Yes, so Noether's theorem, okay, so a transformation in general can depend on many parameters, right? Like rotations in 3 dimensions, right? They depend on 3 different angles, right? However, you can always concentrate on a 1-parameter family of transformations, right? So like, for example, in rotations, right? Any arbitrary rotation can be written in an axis angle form. So you can always think of a rotation as depending on some 1-parameter family of transformations, even though a general transformation is parameterized by more than 1 parameter. So Noether's theorem concentrates on 1 parameter at a time. Okay, you're asking about conservation of charge. We'll see that eventually. It's just we need to introduce a lot more machinery to do that here. But yes, we will see that. Okay, so I'd like to just do one example where it's just to stress how general. Oh, my pencil has died, so let me just talk for a little bit while it's charging. It doesn't take long to charge, like honestly, like a minute maybe. So I just want to I'm going to do an example where the transformation like looks kind of complicated, but like you just run through this formula and it's very easy. So it's a really powerful thing. Once you have this general form, you just do it and it just pops right out. While we're waiting for my pen to charge, can we, are there any questions? No questions? Oh, yeah, so I don't think I'm gonna, yeah, okay, yeah, we've been going for like about 2 hours, so yeah, that's kind of long. So what I'll do is I will go quickly, and I don't think we're gonna actually have time to get to second quantization today. That will be next lecture. So it'll be 2 lectures for special relativity and then 2 for quantum mechanics and stepping into quantum field theory. That seems fair. Yeah. Okay, so how much charge do I have now? Okay, I have 10%, that should be fine. Okay, so let's say that this is equal to dt 1/2 mx dot squared minus some number over x squared. And this has a symmetry. Under x goes to lambda x, and t goes to lambda squared t. And if you stare at this, it kind of becomes obvious why this is the case, right? The reason this has some symmetry that looks like this is because dx dt would go to lambda dx divided by lambda squared dt, which would be 1 over lambda dx dt. That would be this, so this term, right, under this transformation would go into 1 over lambda times itself. Sorry, it would go into 1 over lambda squared, right, because dx dt squared would go into 1 over lambda squared times dx dt squared. So this term goes into 1 over lambda squared times itself. And similarly, the alpha over x squared would become 1 over lambda squared times alpha over x squared. So both terms, this means that the Lagrangian goes into 1 over lambda squared times the Lagrangian. But recall that there is this measure here, and dt will become lambda squared dt, but that means that s, which is equal to dt L, will go into just dt over lambda squared dt times lambda squared times L over lambda squared, and then these cancel, so this is just s. So this is the symmetry. Okay, and now let's read off the conserved quantity. Okay, so to do that, we need to expand this transformation around the identity, right? So we have this here, right? And what it means to expand it around the identity is you say, well, lambda is going to be 1 plus some small amount, right? Because that means that when epsilon is 0, you have the identity. So that means that x is going to become x plus epsilon x, and t is going to become t plus epsilon times 2t. And this means that delta x is going to be x, and delta t is going to be 2t. Now, when I compute, now remember I have this formula. This is my L. And then I have dl dx dot is going to be x dot. And then remember my conserved quantity is just this. This is my conserved quantity. Okay, and then this is going to be L minus x dot squared times 2t, because delta t is 2t, plus x dot times x. And then this complicated looking thing is my conserved quantity. And so you can see that the Noether procedure can let you write down a conserved quantity that looks very complicated, but it's really simple because you just apply this formula. Okay, so now let's check. We already argued that this was a symmetry, but let's check that that a term that we talked about is 0. So remember that a is equal to this. Okay, so and remember also that we have this. Okay, and then you just plug all this stuff in. So delta t dot, so if I just plug this in, delta t dot is going to be 2, and then I have the Lagrangian, which is going to be 1/2 m x dot squared minus alpha over x squared plus 2 alpha over x cubed times x. That's this term. And then I will have mx dot times this, which will be x dot minus 2x dot. And then this term is 0 because the Lagrangian doesn't depend on time. And then if I expand this, I'm going to get mx dot squared minus 2 alpha over x squared plus 2 alpha over x squared plus mx dot squared minus 2 mx dot squared. And I see that these terms cancel, and this cancels with this. So I get that this whole thing is just 0 as expected. Okay. Okay, so the last thing to talk about Noether's theorem is we have one caveat. And that's that suppose we don't have a symmetry. We have S of Q prime is equal to S of Q plus dt epsilon times something, which is a total derivative, which I'll call C dot. Okay. Now make epsilon depend on time. And then in general, we will have that S of Q prime is going to be S of Q plus TA to TB dt epsilon A plus epsilon dot B, because we already argued that. In fact, we showed it. When epsilon is constant, we have to recover this, right? And then you can see by comparing them, this means that A is going to be C dot. Okay, and that means that when you make epsilon vanish at the bounds, and you assume that Q is a symmetry or Q is a solution, you'll have S of Q prime will be equal to S of Q plus TA to TB dt epsilon C dot, because A is C dot, plus epsilon dot B. And then because we said that the Q is a solution and epsilon vanishes at the bounds, this is to be equal to S of Q. And that means that this thing has to be, that means that this has to be 0. And this means that C dot minus B dot is 0. So we just have that C minus B is conserved instead of just B. So you can also, you don't have to have S of Q prime be equal to S of Q to have a symmetry that leads to a conserved quantity. You can have it equal to S of Q plus a total derivative. Okay. Okay. The thing is that we've been going for 2 hours, and the next step that I was going to do is I was going to use this procedure to talk about the conserved 4 momentum and why it's a 4 vector, and like in like a very general ground. But I'm cognizant of the fact that people have been here for 2 hours, and that might be best left to the next lecture. Sorry that this has taken more time, but I think Noether's theorem is very important, so I think it is well worth the time to go through it. If people are comfortable staying for like another like 20 minutes, then I can go through it, or I can save it for the beginning of the next lecture.
I would argue to save it because I imagine 20 minutes will not be 20 minutes.
That's a good point. That's a good point. Yeah, okay. Okay, cool. So that's where we'll leave off for now. Sorry that today's lecture was not on exactly what I said it would be, but hopefully people still got something out of it, because Noether's theorem is very powerful, and I think I really showed you every aspect of it here. Many books tend to like go through it very quickly, or like not explain everything about it, and they really should, because it's it's such a powerful theorem, and it's really strange to me that people don't take their time to like show you how this thing works, and like why it works and why it can be viewed as like a simple idea. So I still think it was a good thing that we went through it. Cool, and yeah, and people seem to like it as well. Good. Okay, I'm glad. So next lecture, the tentative plan will be to apply these ideas to a free particle, explain why the 4 momentum is a 4 vector. Spoiler alert, it's a 4 vector because space-time translations themselves are a 4 vector. Okay, you can kind of almost see that already. And then after that, we will move on to discussing the quantum mechanical system of a free particle. It's a 4. Okay. Well, the question, Bubs, is why does it transform like a 4 vector? The reason that it transforms like a 4 vector, for any relativistic. Okay. Okay, you're technically not wrong, but it's not very explanatory. Um, so basically, the idea will be that for any Lorentz invariant system, right, the conserved quantity of a Lorentz boosted trajectory will have the same conserved quantity if you identify the boosted translation, right? So because translations in space-time are 4 vectors, you can show then that the conserved quantity associated with space-time translations is itself a 4 vector. That will be the beginning of next lecture. Okay, thanks for coming.
Clap, 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 clap.
Okay, are there any concluding questions? Okay, it just seems there's just clapping. People seem to like it. That's good to hear. So it doesn't look like there are any questions. So yeah, thanks for coming, everyone, and I'll see you, I guess, next Saturday.
And of course, if any questions do pop up, feel free to ask them in the server.
All right, see ya.